Hello everyone, welcome to my channel. In this video we will learn about multiple access protocols. So multiple access protocol is also called as the medium access protocol. So what is meant by multiple access protocol? So if multiple number of stations are trying to access a channel, that means they want to transfer the data using the channel, then it is called as a multiple access protocol. So if the channel is of a dedicated link between two stations, that is if the channel is point-to-point link, then there is no need of this protocol. But if multiple number of stations are willing to transfer the data using a channel, then we need this protocol, multiple access protocol. Suppose if you consider the Bluetooth, the transfer of data using Bluetooth. Suppose a mobile is connected to a Bluetooth headphone. So here the connection is point to point, right? So the data will be transmitted from the music will play from phone to the earphones, Bluetooth earphones. So here the link connection is point to point. Whereas in the case of the multiple access, so, suppose you consider the Wi-Fi router. So multiple devices are connected to the Wi-Fi router, right? So using the single channel, multiple number of stations are connected to a single router, right? That is the best example, real-time example of the multiple access protocol. So why do we need the multiple access protocols? So if multiple stations access the channel simultaneously, then there may be collisions. Suppose at the same time two or more stations are transmitting the data, means then there is a chance of collision. So that's why we are using the multiple access protocols. Suppose you are using the dedicated link, then data link layer is sufficient. But if you are using if the channel is used by multiple number of stations, then we need the multiple access protocols. The data link layer has two sublayers. The upper sublayer is responsible for the data link control, and the lower sublayer is responsible for resolving access to the shared media. Okay. So here I think the upper sublayer is responsible for the data link control. Suppose if the connection is, if there is a dedicated link between the sender and receiver, then there is no need of this protocol, multiple access protocol. Then data link control protocol is efficient. The data link control protocol is sufficient. But if you want to transmit the data among the multiple number of stations, then we need the lower sublayer that is responsible for resolving access to the shared media. So if the channel is dedicated, then we don't need the lower sublayer. So if the channel is accessible by multiple stations, then only we need the lower sublayer. So this is how the data link layer is divided into two parts here, the data link control and the multiple access resolution. So if the channel is having multiple number of stations, then we need this protocol, this lower sublayer. So if the channel is dedicated link, then we don't need this lower layer. So the first one is enough, right? So here we will see the responsibilities of the upper and lower sublayer. The upper sublayer that is responsible for flow and error control is called the logical link control layer. The lower sublayer that is mostly responsible for multiple access resolution is called the medium access control layer, that is the MAC layer. So here the upper sublayer is responsible for flow and error control mechanisms, and the lower sublayer is responsible for the multiple access resolution, that is the medium access control layer. So now we will see the different classification of the multiple access protocols. So multiple access protocols is divided into random access protocols, control access protocols, and channelization protocols. The first one is the random access protocols. So in the random access protocol, it is again divided into four types: ALOHA, CSMA, it is carrier sense multiple access, and CSMA with collision detection, and CSMA with collision avoidance. So first of all, we will see about the random access protocols. In random access or contention methods, no station is superior to another station, and none is assigned the control over another. So here in the random access protocol, so there not any station is not given any priority here. So all the stations will be having the same priority over the channel. A station that has data to send uses a procedure defined by the protocol to make a decision on whether send or not send. Okay, if a station wants to transmit the data, then it will follow certain protocols to take decision whether to transmit the data or not. So in the random access, so each station will be having the same priority, and in the random access protocol, any station can transmit, and each station has right to the medium. If more than one tries to send, then the collision may occur in the random access protocols. So that is the main drawback here. So there are two features of the random access protocol. That is, the first one is there is no scheduled time for a station to transmit. Transmission is random among the stations. That is why these methods are called random access. So first, there is no scheduled time for the station to transmit. If a station is having some data, it will transmit, and it won't check whether the transmission will be random in the stations. So that is why it is called as a random. There is no particular time to transmit for the station. And the second one is there is no rules to specify which station should send next. The stations compete with one another to access the medium. So there are no rules given in the protocol that allow whether a station wants to transmit or not. So if a station is willing to transmit, then it will transmit. And here there will be some competition between the stations to access the channel, because each and every station will be having its own right to access the channel. So that's why there will be some competition. So each station has the right to the medium without being controlled by any other station. So if more than one station tries to send using the channel, then there is an access conflict, collision, and the frames will be either destroyed or modified. So if more than one station accesses the channel and tries to transmit the data, then there will be there will be collision. Okay, now the data will be modified or destroyed if the collision occurs. So next one is we will see the different types of random access protocols. The first one is the ALOHA. ALOHA is the earliest random access method. It was developed at the University of Hawaii in early 1970s. It was designed for a radio LAN, but it can be used on any shared medium. So this is the earliest random access method, ALOHA. So it is developed in the University of Hawaii in 1970, and basically it is used for the wireless LAN, but it can be also used on the shared medium. So there are two types of ALOHA, that is pure ALOHA and slotted ALOHA. So first of all we will see the pure ALOHA. So ALOHA, the original ALOHA protocol is called pure ALOHA. The idea here is that each station can send a frame whenever it has a frame to transmit through the channel. So there is only one channel to share. There is a possibility of collision between the frames from different stations. So the original ALOHA protocol is called as a pure ALOHA. So here, if a station has a frame, then if it is willing to transmit, then it will transmit by accessing the channel. So since there is no protocol or agreement between the stations which are accessing the channel, so there will be a chance of collision. So let us see the example of pure ALOHA. So here we are having the four stations that are sharing with a single channel. So this diagram shows that each station sends two frames. Right? Station 1 is sending 2 frames, station 2 is sending 2 frames, 3 and 4. So each station is sending 2 frames, and there are a total of 8 frames on the shared medium. So some of these frames may collide because multiple frames are in contention for the single channel. And this diagram shows that only two frames survive, that is the frame 1.1 and the frame 3.2, and the remaining frames almost coexist with another frames. So frame 1.1 from station 1 and frame 3.2 from station 3 survive, and the other will get destroyed. So we need to mention that even if one bit of a frame coexists on the channel with one bit from another frame, so there is a collision and both will get destroyed. The pure ALOHA protocol relies on the acknowledgement from the receiver. So the pure ALOHA depends on the acknowledgement from the receiver. So when a station sends a frame, so it must receive the acknowledgement from the receiver that the frame is successfully received. So if the acknowledgement is not sent, then it will consider that the frame is lost. So when a station sends a frame, it expects the receiver to send an acknowledgement. So when a station sends a frame, it expects the receiver to send an acknowledgement. So if the receiver is not sending the acknowledgement, then it considers the message is lost. So each station waits a random amount of time before resending its frame. The randomness will help avoid more collisions. We call this time the back off time, TB. So each station will wait a certain amount of time. It will switch on a timer after while transmitting a frame. So the acknowledgement must be received from the receiver at a particular amount of time. So that time is called as the exponential back off time. So this will avoid more collisions. So if you are using the exponential back off time, so it will set a particular time limit. So within the time limit, it must receive the acknowledgement. Okay. So that random amount of time is called as a back off time. So using this flow chart, we can consider how the pure ALOHA will work. Here the station is having a frame to send through the channel. Okay. So it will send the frame. So the k is equal to 0. It will send the frame and it will wait for a certain amount of time, which is the 2 times the propagation time. So the timeout period is equal to the maximum possible round trip propagation delay, which is the amount of time required to send a frame between the two most widely separated stations, that is 2 times the propagation time. Okay. So wait of time is 2 times the propagation time. So we will see about what is the propagation time in detail. So if the acknowledgement is received from the receiver, then the transmission is successful. So if the acknowledgement is not received from the receiver, then the transmission is considered to be failed, right? So it will increment the k value by 1 and it will choose a random number between 0 to 2 power k minus 1. So it will wait for a particular time. So after a maximum number of retransmission attempts, k max, a station must give up and try later. So here k max is normally 15. So in this method, for each retransmission, a multiplier in the range 0 to 2 power k minus 1 is randomly chosen and multiplied by Tp, that is the maximum propagation time, or T frame, that is the average time required to send out a frame, to find the exponential back off. So in this procedure, the range of the random numbers increases after each collision and the value of k max is actually 15. So we will see the vulnerable time and throughput for the pure ALOHA. So the vulnerable time of pure ALOHA is 2 times the frame transmission time. So vulnerable time means the time where there is a chance of collision between two frames is called as a vulnerable time. So that is 2 times the frame transmission time. So if you see the diagram here, so in the given diagram, so here the two frames, that is frame 1.2 and frame 2.1, are colliding with each other, right? So that means the ending of the first frame and the starting of the second frame are colliding with each other. So the chance of collision, the time where the collision happens, is 2 times the transmission time, frame transmission time, right? So the ending of the frame 1 and starting of the frame 2 are colliding with each other. So this is called as the vulnerable time, which is 2 times the frame transmission time. And in pure ALOHA, the probability of successful transmission of the data packet, that is equals to G into e power minus 2G. So where G is the average number of frames generated by the system during one frame transmission time. And in pure ALOHA, the maximum efficiency is equals to 18.4%, or G equals to 1 by 2. So in other words, if one half of a frame is generated during one frame transmission time, so one frame during two frame transmission times, then 18.4% of these frames reach their destination successfully. So this is an expected result because the vulnerable time is 2 times the frame transmission time. So therefore, if a station generates only one frame in this vulnerable time, the frame will reach its destination successfully. So the pure ALOHA doesn't reduce the number of collisions to half. So this is all about the pure ALOHA. Thanks for watching my video.